Okay, this is for tutorial 2, question 2.79. So we have in each lot of 100 items, okay, 2 items are tested and the lot is rejected if either of the tested items is found defective. A, find the probability that a lot with K defective items is accepted. So in this question, you have 100 items, okay, and then you for every 100 items, you perform 2 tests. So the first test, you check if it's defected or not. If the first test is passed, then you perform the second test, right? Okay. So you do one at a time. Now we are asked to find the probability that a lot with K. Okay, it doesn't. We don't know how much K is, but out of this 100, you have K defective, and the rest 100 minus K are non-defect. Okay, all right, that's understood. So you want to find out what is the probability that when there is K defective items, they the slot of 100 will pass the test, meaning that the first test a non-defective is chosen, the second test also a non-defective item is chosen. So let's write down this statement. If we put A1 as a non-defective item is found in the second test, and A2 to indicate the event where a non-defective item is found in the second test. Okay. So we have K items that are defective in 100 lots. So the probability of A1, which means that a non-defective item is found, meaning the probability that you choose a non-defective item. So there are 100 minus K non-defective items divided by a total of 100 items, right? Okay. So if I draw a tree diagram, okay, because it's a sequential process, a sequential experiment, you perform the first test and then the second test. This is what it look like, okay? So A1 is non-defective items found, okay? So here we have the probability of A1 is 100K minus 100 as before, and A1 bar is the event where a defective item is found. So we have K defective over 100, right? So when if you pass the test, if you obtain A1, then you can proceed with the second test. But if you found a defective items on your first test, then completely you stop the test. This is because if you look at the question, the lot is rejected if either of the tested items is found defective, meaning that either first test uh, is if you do the first test, it doesn't pass, you reject the lot, or if you do the first test, it passed, and then the second test it did not pass, then you also reject the lot. Okay, it doesn't have to be 2 items both defective that you reject. It's either a 1. Okay. So in this particular case, uh, here you reject, right? Because the first test is a defective. Now in the second test, if you also get a defective items selected, then here also you reject. Otherwise, if you pick A2 where A2 is a non-defective item found, then this one you pass. Okay. So here the probability that you get a non-defective items on the second test, given that A1 is also a non-defective items, because you reach here only after you obtain a non-defective item on the first test. Okay, so it's conditioned on A1, right? So this is the value is 99 minus K over 99, right? So how did I get this value? Okay, once you reach the first test is a non-defective items. So what's remaining in the batch are 99 items. Out of the 99 items, the one that you have chosen is a non-defective. So you still have K defective items in your lot. Okay. So the probability of you choosing a defective items in the second test becomes K over 99, whereby choosing a non-defective items is 99 minus K divided by 99. Okay, so if you add these two up, you get 1. Similarly, if you add these two up, you also get a 1. Alright, so the question is asking, find the probability that a lot with K defective items is accepted. Okay, so the probability of A1 and A2, right? Okay, so from here, the probability of A1, A2 is probability A2 given A1 multiplied by the probability of A1. This is 99 minus K over 99 multiplied by 100 minus K over 100. Okay, so this is the probability that the lot passed the test. Okay, for the second question, suppose that when the production process malfunctions, now 50 out of 100 items, okay, are defective. Okay, so now the probability from 100, you have 50 defect as well as another 50 is non-defect. Okay, good items. So in order to identify when the process is malfunctioning, okay, how many items should be tested so that the probability that one or more items are found defective is at least 99%. Okay, so in this question, they are asking you how many items should you test so that the probability that one or more items are found defective is at least 99%. So if we were to write the probability that it's asking, you can say we were asked to find the probability that one or more items are defective in M test. We don't know what M is, and the probability of that is at least 99%, so bigger than 99%. So in other words, oops. Okay, so in other words, the probability that none are defective in M test is less than 1%. Okay, because this is the conjugate of the first statement. Okay, so here what it's saying is that if we perform M test, okay, what is the probability that when you reach the M test, all of it is passed, is less than 1%. Okay, so we can draw this in like a tree diagram as well. Okay, so let's say we have the first test A1. Okay, so the probability that you pass the test is 50 over 100 because there are 50 items that are non-defect. So A1 is non-defective item. Let's put it as AI. Okay, non-defective item chosen on the I test. Okay, so we have A1 here, and then this is A1 bar, right? So if the first test is non-defective items chosen, then again you choose another one. Okay, so we have A2, and this one becomes how much? 49 over 99, and then A2 bar is 50 over 99, correct? Okay, so A2 is non-defective item chosen on the second test. A3 is 48 over 98, and A3 bar becomes 50 over 98. Okay, so we are looking at the case of this. If you have A1 and then A2 is chosen, A3 is chosen, then these are all your probabilities. Okay, and then we proceed some more, and this is A4. Okay, A4 bar, this is 47 over 97, and this one is 50 over 97, right? Okay, so we are trying to find the M test whereby the probability of all non-defective items are chosen until M test is less than 1%. Okay, so how do we write this? Okay, so if we do only two tests, okay, so probability that non-defective items are chosen in both two tests, or it passed the test, let's say until two tests, just two tests. So PA1, A2 is equal to 50 over 100 times 49 over 99. How much is this equal to? Okay, so if we take M equals to T, whereby we perform three tests. So let's look at the probability that none of the tests obtain a defective items, right? So in this case, if non-defective items are chosen in three tests, so you multiply this with this and this, right? Okay, just the same way as how we did for the two tests. Okay, so in this case, non-defective item chosen in three tests, what we found is 0.12. So it wants to know what is the M that gives you less than 1%. So this 1% is 0.01. So of course, this is much more bigger than 1%. So let's do next. We perform for M equals to 4. Still, we have this same multiplication and we add one more. Okay, which is 47 over 97. Okay, multiply with that, we get 0.05. So let's say we skip a few steps and do when M equals to 6. Okay, so you can imagine if M equals to 6, so you have the fourth test and the fifth test. So all of that branch are referring to non-defective items chosen on their respective tests. Okay, so I didn't draw until 6, but you can do that, right? So when you have 6 tests, okay, you include all these values and you found it to be 0.013. So 0.013 is actually still bigger than 0.01. So we do one more, okay, non-defective in 7 tests. For 7 tests, we found that the value is 0.006, which is indeed less than 0.01. Okay, so the number of tests that we need to perform is 7 tests to ensure that okay, so if we perform 7 tests, it's less than 0.01. So we can see that the probability of one or more defective in 7 tests is equal to 1 minus 0.06, and this is equal to 0.994, which is bigger than 0.99, which is the required condition, right? If we stop at 6, okay, then what is the 1 minus value? 1 minus 0.013 is equal to